Okay, let's kick this off because we started a bit late this morning. Matt and I are here today. We're going to talk about reactive GUIs, so please stay, don't all leave. I'm guessing there's quite a lot of server-side guys here. Remember what you guys do, so it has to be rendered somewhere so someone can click on a button. My name's Campbell. I'm the author of Intro to RX, Reactive Extensions, which is a similar topic to what Andy was just talking about. I work with Matt at Adaptive Consulting, and we're consultants to the finance industry at the human scale mainly, so building graphical user interfaces so humans can do trading, in contrast to what sort of Todd and Martin are doing, which is computers trading with computers. Matt.
Thanks, Lee. So I'm Matt. I work at Adaptive with Lee. And as Lee said, we build financial services applications, GUIs, middleware and backends. And today we're talking about user interfaces. And we're looking at user interfaces through the lens of the Reactive manifesto. Like Lee said, we've heard a lot over the last day and a half about high-performant, resilient, elastic, and responsive systems sitting in the cloud in a private data center, no nines of availability because we've solved all our failover and resiliency problems. We've put all that effort into building a wonderful back end, and someone forgot to build a user interface. Someone forgot to tell the users to load up the application and actually come and use our application, buy our products, buy our services, interact with us. So what we do at Adaptive is we build reactive user interfaces that work well with the sort of scale of the back-end systems that and architectures that the back-end systems that we're talking about over the last 2 days that these guys build these systems. So Reactive Trader is an application we're going to use a bit later on to demo some of the concepts that we will be talking about. Because we build user interfaces, we thought it's slightly more interesting to talk about user interfaces and show them at the same time. So we've put something together. We used it earlier this year when we spoke in London, but slightly different talk. We're more going to talk about the attributes of those applications in general rather than the specific ways in which you can go about doing it. If you want to hear more about the specific ways of doing it, please come to our workshop tomorrow. We'll dive a lot more deeply into all of this stuff and hopefully have a really good session. So Reactive Trader, online at reactivetrader.com. There's a web app, a WFF app, and an iOS app. You guys can all pull it up on your laptop now, play around with it. Depending on how well things go later on, we'll do some interactive demos so that you guys can all trade and see things on screen, and we can turn prices on and off, and we'll see just how this reactivity plays out in the real world.
Cool. Okay, so this is how we're going to do the talk today, split it up and look at it through the prism of the Reactive manifesto, which I think now that it's had a little rewrite, it maps a lot better to what we're going to be talking about. So first off, we're going to start off with message-driven. Can you tap through? Cheers, Matt. Sorry. All right, so I want to talk about a continuum of maturing from methods, callbacks to message passing. So I think in most code, you're going to be writing synchronous method calls, and that's a really great thing to do. As Martin will talk about, whenever you're writing high-performance applications, single-threaded is really fast, great. Problem is when that becomes the only hammer you've got, and then when you try and do I/O, and you try and talk across bounded contexts, and you're doing that with synchronous method calls, you're going to fall off the cliff, and we can't be doing that in the UI, and we'll talk about that later. Then we can sort of upgrade, move along the continuum a little bit, and products like Node.js, where callbacks is a part of the functionality. So potentially long-running things like I/O, we sort of say, this is what we'd like you to do, call me back when you're done, and then you can carry on, and it kind of feels like a natural flow. When you get to crossing of boundaries, as Ben was talking about yesterday with the Cedar architecture or the disruptor actor pattern, as soon as we cross a boundary, let's create a message and pass that message. So if we look at the properties of messages, we're talking about data, not method pointers. Okay, they're queued and they're processed asynchronously. Todd also talked about other features of messages, so we won't cover those now. But Matt can talk to us about what's not message-driven then.
Yeah, so when we sat down to think about message-driven applications and the parts of the user interfaces that we build, the user interface applications that we build that are message-driven, we kind of struggled to think. We couldn't really see the wood for the trees because we've been building applications like this for so long, streaming prices to client UIs, dealing with configuration changes, dealing with entitlement changes throughout the day, throughout market open everything is message-driven. So I went back to basics a little bit and thought about what isn't message-driven. And it ties in really well with what Jonas said. Message-driven is CRUD. Create, read, update, delete. Synchronous calls into a database from an application that go away. Some select query that pulls in a big graph of data back out via an ORM, an object relationship mapper that lets us squint and pretend that we're dealing with an object graph in memory when in fact we're dealing with relational tables that are stored in some other machine in a database that we don't control. So that's not message-driven. How does that map to a message-driven world? Well, Andy talked about this 5 minutes ago. It's about streams of data that we push from the server to the client. And what does that look like? It looks a little bit like this. This is the old world. My diagram is pretty bad. I'm quite happy to admit that. Todd had a fantastic diagram yesterday of a big, complicated entity relationship mapped diagram with one-to-many relationships and many-to-many relationships and big, huge, thick, interdependent thing that's all got, that if you had it in memory, it would all be a bunch of pointers and a bunch of state laid out on the heap somewhere. This is a much simpler version of that, just so that I can think about it. What we have when we go to event-driven applications that have some sort of CRUD-style functionality in them is that we replace our database with a streaming server, and we push streams of data, so changes in entities, changes to an accounts table, changes to a trade database, changes to a user model, from the streaming server to the UI. And we do that all on independent streams, which has some interesting properties. We'll talk about that in a second. But the key thing that we do at the other end in the UI is when we receive all these different streams of data, we cache them locally. So we're replicating now, basically. We're replicating server state from the server to the client, which has got some fantastic properties. One of the things we need to be able to do to ensure resiliency. And we end up with a system that has this asynchronous observable model in our UI that has some really interesting properties. For one, it lets us do small isolated updates. So that big graph that Todd showed us yesterday, if we wanted to talk about or reason about some small change deep down inside that object graph where one value changes, typically what would have happened in the old world is a user would hit refresh, go back to the data, we'd throw out the model we had, we'd go back to the database, load the whole thing up again, bring it back. A huge amount of extra work that we don't need to do if we're in this event-driven world where we're pushing individual changes from the server to the client as soon as they occur. Really nice. Makes a much smaller amount of traffic on the network for one thing. In this mobile-first world, can't be a bad idea. It's not all great though. As Todd talked about yesterday, order is a complete illusion. If we're pushing streams of messages from a server to a client, an individual stream might arrive in order, may not. We have to deal with that as well. That's not really the point. But we will probably have out-of-order arrival of different, but amongst different streams. So a trade might arrive and it might have a pointer to an account, and the account stream may not have yet yielded that particular account entity. So we sit there with a bit of a problem where we've got some object that's talking about some other object that doesn't exist. So what do? Well, we have to make our domain model, that is the thing we program against in our client UI, asynchronous. So instead of having a big, thick, heavy object graph that you can dot through from client to orders to line items to quantities, lots of properties on objects, really simple stuff that we get from an ORM kind of for free. All of that stuff in different tables gets pulled back and we work on it synchronously. We end up with an asynchronous domain model. We're going to do a demo later on, at the very end actually, that talks more about what an asynchronous domain model actually means and how you would go against working with it and how you need support in the language to really do the right thing with it. That was something that will probably highlight these concepts a little bit more. But it's important to also realise that these streams of messages that we're sending, many of them down to the client, they go both ways. We don't just push messages to the client and then do synchronous request response from the client back to the server. That's totally not the right thing to do. These are all kind of enterprise messaging pattern concepts that now no longer we now no longer can just ignore because we're not enterprise guys dealing with a whole bunch of boring servers sitting on premise at some company's data center. We're now talking about how user interfaces and applications are getting richer and more engaging, and that they are kind of operating in they're more closely tied to the server infrastructure in which they run. So enterprise messaging patterns of pub/sub, what I'm doing now, publishing, you're all hearing the things I'm saying, and one-to-one, where Lee and I can bounce messages back and forth. All these sort of styles of communication are layered on top of low-level messaging primitives, exactly like Andy was talking about. He was talking very much in the large. We're talking more in the small, from the point of view of a single application that we need to write and deliver to our users, a Netflix UI, for example. And all of this stuff is asynchronous. Like Todd said yesterday, message-based architectures are great not just because of what they allow you to do, they're pretty good at what they stop you from doing. And they make it really hard to make blocking synchronous calls into a database. We just had a wonderful talk by Andy on streams of messages. I'm not going to go over this slide. When we're talking about messages, we have bunches of them. They're ordered in some sense. That makes them a stream. We're clearly people that have made very heavy use of reactive extensions. Ben just pushed version 1 of RX Java out yesterday. Congratulations, Ben. Well done. Yep. Very long road you guys walked down, and a lot of a future ahead of it as well, from the sounds of things. But we've been using RX on Microsoft platform since it came out 5 years ago yesterday. So we're big proponents of it, and it makes streams first-class concepts in our applications. And you're about to see what Reactive Trader looks like, and that will kind of give a bit of context to everything being a stream.
So here's Reactive Trader in action. It's just demoware, it's not a product we're trying to sell or anything, it's just something that allows us to talk about something concrete. So here we've got foreign exchange prices. We're from London, we came over here to the States, we're going to need to swap British pounds for US dollars. UIs like this enable people to do that at massive scale. So the guy that's buying all the silicon chips for Apple, if he's buying that, he's going to make a massive FX transaction. This is who this kind of product is targeting. Okay, so Andy talked about streams being conceptually infinite. We've got some examples here. Prices are being ticked, they're being pushed at us. We're not asking for these prices. We've subscribed once and these prices are being pushed at us. You can think of that a little bit like the Twitter fire hose. So these are being pushed at us, and as Eric Meyer would say, Hadoop's not big data, infinity's big data. So we've got some infinite streams coming down here.
And some very time-sensitive ones as well.
Yeah, exactly. So people need, these prices can't be stale. So we've got prices coming down. We can execute on a price, and that will say, hey, I want to trade on that price. We send a message back to the server. The server accepts it or rejects it. In this case, it's accepted it. We get confirmation here, and our state is updated down here, okay? So we've got another interesting point here, is if we started up and there was actually trades already in our blotter here, our trade log, we would have that problem of how do we get data at rest and moving data at the same time, so we call that the state of the world problem. If you're using systems like event stores, as Jonas talked about, greatly improves your life. If you're trying to mix REST data from a SQL Server database or something like that and moving data, it becomes very difficult. So we've got prices coming down, trade executions going up, trade responses coming back. We also have this little server that we run here to allow us to model the application. And here we also, we can sort of fiddle the bits over here, because this is all a mock environment running on this laptop. We can also say that changes in state, not just the price themselves, but the availability of the price is a message. So here we can see Euro USD is available. I'm going to whack that button, turn it off, and we'll see that it disappears, okay? We'll turn it back on, and down the bottom of our chart, we'll see that it appears again. Okay, so we've got not just prices, not just trades and execution, but actually the state that your application can be in, all as part of messages. Now, we're doing the right thing at the moment. We're doing everything asynchronously, but just as a contrast, this is what happens if you try and do stuff synchronously. So we can see there's a lot of movement on the UI right now. If we try and do a blocking call to make a trade, note everything freezes. We get a global pause, sort of like what Gil was talking about in the GC. We don't want this, and we can't even have it on the UI, okay? So that's message passing in the UI. So the global pause also gives us a nice lead into talking about responsive.
So message-driven, I guess why is it interesting to talk about message-driven architectures and the concept of it when it comes to building user interfaces? The answer is that with the sort of applications that Reactive Trader fits in with, there's no other choice. You can't poll, so you have to be message-driven. And I think more and more applications will be going this way in the future. Your Facebook feed, your Twitter feed, all of this stuff is streams of data. It's real-time, and everything from that will flow. All our applications in the future will be near real-time, as Martin says, squidgy, some more valuable than others. So responsive. Pretty clearly, Reactive Trader needs to be responsive to changes in market movements in the prices of various currency pairs. Those streams of prices can be very volatile. They can be slow-moving or fast-moving, and they can be very bursty. And all of this stuff is a reality, and we can't do anything about it. The streams are very time-sensitive. We can't queue. If we are queuing, we really need to understand what our mechanics are for dealing with that extra work that we've bunched up, which we'll talk about in a second. So we've got the possibility of there being far too many prices. We connect to a server, and there's some guarantee that it'll send us 10 or 20 messages a second. Okay, that's great, but we've got a distributed architecture. We're talking inside Netflix to thousands of different, or hundreds of different services. Each one of them has an opinion on how many messages a second it can send. Put that all together, and there's probably going to be too many messages coming out of the infrastructure down to the client. So the client needs to be able to do something as well to make sure it can remain responsive. To what? Responsive to what? Why don't we just stick a UI up and not let the user do anything, have a dashboard? Well, it's not a dashboard. It's a user interface that is designed to allow people to trade, to buy into and out of currency positions, and we get some very angry users who don't want to be holding on to $1 million when the US dollar tanks. Our applications need to be responsive and remain responsive under high amounts of load. It's not just ticking prices and clicking buttons, it's also the fact that users have got really high expectations. 10 years ago, 12 years ago, you could afford to build a very ugly application, especially in the financial services. You could afford to build an ugly application and people were just kind of thrilled that it existed at all. That's not the case anymore. Consumer IT, consumer computing, Apple-inspired interfaces, everything has to look good and make users feel good about using it. So Reactive Trader has got some of that in it, and when we do a demo, we'll talk about how those extra UI functionalities, the buttons fading in and out and mousing over your visual elements, causes responses, makes people feel like the application is actually alive underneath them. All of that stuff has a cost, and it's all coming from a single shared resource, which is the UI thread. So single-threaded UI applications, we all understand that that's just the reality. There's lots of good research that's gone on to the topic of making it not true. No one seems to have succeeded. Take a look at that later on, or come and chat to us later. It's quite fascinating. And of course, all these actions that people take are inherently asynchronous. We can't live in a world where we just stop the application, stop all the code that's running, go off and wait for the server to tell us if the trade we tried to do succeeded or failed. It's asynchronous by its very nature because it's message-driven. Now, it's all well and good, but like I said, we've got a very high-frequency server world where we're sending millions and millions of messages a second, and then we've got our screens, which are rendering at 60 frames a second. That's already a massive discrepancy. And then we've got us, humans, who are sitting there trying to make intelligent decisions about what we should do. Should we buy? Should we sell? I'm not sure whether you guys remember Lee's screen. It was 100, 200 messages a second.
Yeah.
It's already pretty hostile, and it doesn't give you a lot of confidence that what you click on is actually going to be what you buy or sell, the price, I should say. Gil talked a lot yesterday about latency measurement. If you guys go to humanbenchmark.com, if someone brings that up now, I'd be really interested if we just did a really quick test. It's a really simple web app that lets you figure out how quick your reaction times are. I think this gentleman here is going to give it a go. I know how quick my reaction times are, very slow. I'm surprised I managed to walk up the stairs.
Like an old lady.
Like an old lady, yeah.
You can't trade.
Exactly. It's quite fun. It just simple, shows you how long it takes to click a button when the screen changes colour. People get 200, 300 milliseconds. That's a really long time in computer world. So why are we worrying about forcing a fire hose of information into a user interface when you can only respond in the order of about half a second? We're not going to wait for you to do 1 million tests so we can find out your 99.999 percentile. That would take a very long time. But the point remains, humans are slow, computers are fast. We've got different scales operating here. So, going from high-frequency price movements with a lot of fine granular detail to slower moving ones that can be consumed and understood by humans is called conflation. Well, going from high frequency to low frequency is called conflation, and in financial services applications, it's the prices that do that. We're explicitly limiting the throughput from a frequency perspective. We're not saying that we are saying that we have to do something about the fact that we can receive 1,000 messages a second. We need to slow that down. There's a bunch of different implementations. There's some in Reactive Trader that we'll talk about momentarily. But the point being that it also kind of introduces latency, which we want to avoid at all costs. Gil has got a fantastic system where you have consistent low latency. That's the dream. But one of the things he talked about was hitting that SLA that you signed up to when you delivered the application, of maybe paying a bit more over all your operations, so your latency goes up a little bit, up to the 90th percentile, but the fat tail of very slow things over and above 99.995, that goes away. So switching from very low latency to consistent latency is one of the things we do when we start thinking about conflation. Lee,
So
let me swap
let's
over.
talk about creating a convoy. So people that do concurrent programming are probably aware of this. It's effectively creating queues inside our systems, and as Martin talked about, queues that we don't control. So imagine we've got a sequence over time and we receive a price. A price tick comes in from the server, and this yellow-orange box here represents the time that it takes for us to render that price. I mean, it's pretty quick, but it's not free. There is some time it takes to render that tick. And another price tick comes in and we render that, and another price tick comes in and we render that. The problem comes when this happens. We've got this period of time where we're rendering price, and we've got two more prices come in. The naive approach is to take price, we've got 1, 2, 3, 4, and re-render price 4. But as we start rendering price 4, I've already got price 5. I'm rendering stale data. So then I render price 5 again. What becomes very interesting here is if this happens at scale, say someone clicks a button in here, the way that UIs normally work is that when you click, these two actions have probably already been scheduled. Your command will be executed over here. Which price are you actually executing on? So we've got a problem there, okay? So that's creating a convoy. What we'd like to do is to avoid the convoy. First, we'd like the server just to, based on its SLAs, not send us bursts of information like that. But there's networks and things that get in the way, so we can't always be guaranteed of that. So the more obvious thing to do here is to conflate. And we just do one price tick here. Now the question is, do we merge those two prices? Do we take the last price? That's a business decision you'd need to make, but we're trying to do the right thing by the user here and not drowning their computer, not flooding their computer. Okay, so let's see Trader in action.
So back into Reactive Trader, where we're publishing 100 messages a second, and projector's quite good, so you guys can see that we've got some of these visual embellishments, I guess you could call them, that make the application look like it's responding. We move the mouse around, things respond in time, which is fantastic. Actually, everything has just stopped working at that rate anyway. So one of the things we've built into Reactive Trader is different ways of conflating prices, of getting the frequency from very high to not necessarily very low, but something we can deal with. Drop frame is exactly what Lee was talking about just before. This is where individual prices come in and are queued. Now, like I said earlier, all these asynchronous message boundaries that we have inside our applications, they all imply queues where things wait for the other system to be able to start picking them up and processing them. If we look into the nature of price streams, it's pretty apparent that rendering the 3rd, 4th, 5th, 6th price, which is out of date because we've already got the 7th, is not the way to do it. And that's what drop frame does. Drop frame is a technical implementation underlying the code built on top of an RX stream that is very simple when you think about what it is that you actually need to do. But the effect of it is that by reducing the amount of work we do at higher loads and looking into the streams and throwing away prices, we can keep things moving along quite a bit better, which is always very awkward on this little machine that fails to respond completely. the point being that we throw away prices so that we don't have queues backing up. And you can see here that we're publishing about 300, we're receiving about 300 updates a second down the bottom, and we're actually trying to publish quite a bit more than that. So we've got a queue building up, which means the system isn't working as it should. Now, this little laptop doesn't do a very good job of demonstrating it, but if you guys come along to the workshop tomorrow, we'll talk more about this, and we've got diagrams and we can play with it on real machines that make it really fly. Was that the only?
So we've got so it doesn't have enough Apple stickers on it to run fast enough.
So that's conflation, and there's other ways we can get around that problem as well, and we'll talk about one later on when we talk about elasticity. But for now, let's go back to talking about resilience.
So moving on to the third pillar of the Reactive Manifesto, resilience. Resilience becomes interesting in a user interface application because we've generally got some different approaches to what you would do if you're working on the server side. But the three patterns are still kind of the same. So we've got replication, isolation, and degradation. So we can do replication, we can have local state stored on the client. Isolation, well, we're already doing message passing, so we're not doing these synchronous calls out to systems that are blocking. And degradation, we're going to talk about that in a little bit more. So I think there's a continuum of maturity, again, on how you deal with errors. So I think the basic thing that everyone will sign up to is that you validate your inputs, you check that the user's actually allowed to do this kind of thing, and that you've got some business flow. We're talking about overbooking by 115% as a business rule. Some of these rules will live on the server, so when we say we'd like to execute a trade, the server's going to have more knowledge about whether that person can do a trade or not. Is the price still relevant, or have we sent them an old price? Is there enough liquidity in the bank, so is there enough stock on the warehouse? And has that person got enough money? So they're going to do some checks, and we can expect that potentially we can get a trade rejection. Now that's kind of the minimum thing we're going to expect to see here. What we also can see is that we might get missing messages. We're into an asynchronous environment now. We might send out a message, a trade command, and just not hear back. So what we're going to do there is inject into our own incoming message stream a trade failure, okay, or a timeout. We might also, on our price ticks, not get anything for an SLA of, say, 4 seconds, in which case we need to identify ourselves at that stale and, again, inject into our message stream that the price is stale. So then there's another thing that could happen is just outright failure. So it's not a little case of there's some silence on the wire, we've just lost connectivity to the server. So in this case, we're going to lean on our middleware. The middleware is probably going to tell us that there's been some sort of severed connection or that the server's not available. That's available even in the cheap free stuff, so that's really good to have. We're going to then degrade, hopefully, certain aspects of the application. So maybe it's just the botter or the trade log is not available, in which case we'll just degrade back to showing what's in our current state. Or when we load up the application, we can read off something persisted to disk. If it's the prices, we'll go stale and say, look, at the moment there's no prices, maybe here's the last known good prices, just so you've got a general indication.
I'll do this as well. I'll do the next bit as well. So I'm really pleased. I really love coming to these sorts of conferences, React, especially because we get to do a lot of cross-pollination of concepts. At least from my perspective, building primarily UIs and things that sit outside of the data center that deal with clients who aren't trusted, we have different concerns. It was really interesting hearing Pat yesterday talk about apology-oriented computing. It's such a fantastic way of thinking about the systems that we need to build, and then to have it backed up later on that evening with the high availability no nines talk and how you get to that, and is it possible? And yeah, I think it is possible, but I think we all need to as technologists sort of rethink the bounds of the service layer of what actually we're trying to do, and that technology isn't a means to itself, but it's a means to enable some other business process. So Reactive Trader is about trading foreign exchange. People have been trading foreign exchange for hundreds and hundreds of years, long before we had cloud-based architectures and nice touch screens and all the other trappings of modern consumer technology that we all know and love so much. If everything stops, if the data center goes down, if both data centers go down, if the trade response doesn't come through, there's still someone sitting in the trading office at the trading desk, most likely in London or in Singapore or in New York, probably distributed as well, so they'll have 2 trading desks available at the same time. If the technological system goes down, let's just get the user to call and make the trade, right? That's fantastic. We're taking technological failure and treating it as just another business event. And that means we've kind of increased the availability of our system from just what we can achieve on the computing world and turned it into something that spans a bunch of technology stacks so that the phones keep working, ideally, and they can ring up and make a call. For the sorts of applications that we build, it's kind of clear that if we click a button, make a trade, and don't hear anything back, something's gone wrong. But actually the sophistication goes a little bit deeper than that, in that we actually do a reverse acknowledgement. So that if I try to do a trade, the server tells me that it received the trade and, yep, I'm in or out of the market. I then need to go back and send a response to that, an ACK to the ACK basically, go back to the server and say, hey, thanks very much. Thanks very much for telling me what I tried to do worked. I'm really pleased we're all agreed. Sort of like a 2-phase commit for the actual financial deal, the business process that's going on underneath it. That's not something you do for all the messages you send back and forth. It's just not interesting, right? It introduces too much latency. It's a far too high level of service. But for high-value business transactions, that's really important. And what that means is that at the back end, you can have a business process that kicks into action when that second acknowledgement doesn't come back, and that's exactly what happens. A salesperson sitting on a trading desk will get a message, an alert pop up on their screen or an email or what have you, told the number to ring, and they'll ring the client and say, hey, we saw you just did a trade. You probably don't know what happened. This is what happened. No nines? Have we got 100% availability with this sort of system? Maybe, we're getting close. But it's about understanding that computers make mistakes, that we have to build technical apologies into the workflows, and we need to understand how all of this ties together, both for the business and for the technology, for the UIs that we build.
So this is especially important too when you don't own the full stack. If there's the internet in the middle, and you've got things like Azure that can't even stay up last night, it's going to be difficult when some of our clients in Asia just don't have good enough internet connections to make that trade. That telephone still has to be a valid option.
So what does this look like from an application perspective? How do you go about putting this on screen? So we've got a bunch of different currency pairs that we're streaming live here, and you can see they have different result states. If you've got this on your laptop or on your iPhone or whatever, all these rules are the same. It's just that this server is running on this laptop, whereas the ones you guys are playing with is out running on Azure. Is Azure up now, Lee?
I hope so.
Who knows? Those poor guys, there'll be some very unhappy system admins today over there. So what we've got is a bunch of different currency pairs that respond in different ways. So USD JPY is just a normal currency pair. We do a trade, we get a response. Let's click that back to being asynchronous. We do a trade, we get a response, something appears in the blotter. It's not particularly exciting. But for Euro JPY, what we have is the understanding that there's an SLA built into the stream. So there's a business process that says, a business discussion that goes on that says, if you try to do a trade, we will tell you whether or not that succeeded or failed within 4 seconds. That's the SLA across the platform. 4 seconds is quite a long time on a computing scale, but there might be a trader sitting there for a really large trade making a human decision about whether or not to actually do the deal with you. It's Euro JPY. So we can see that Euro JPY takes a long time to respond. The UI says that something's gone wrong, and then we get the response. So this apology-oriented computing concept is kind of brought to life here on a very short timescale, which is great because we can talk about it and conceive of it, and we don't get an email a day later saying, actually, it's not shipping tomorrow, it's shipping in a month. So we do a trade, the UI responds immediately to the user's input. It took longer than 4 seconds, so we changed the UI, and then a second or so later we get the actual trade request that comes in, and the UI flips over and says, hey, trade was done, everything's good, back to normal. It's message-driven, and it's resilient, and it's apology-oriented, I guess. I mean, this is the point, right? These are really good concepts that we can take, and it's good to be able to have them enunciated so that we can talk about them and all understand that this is the sort of applications that we need to do. So we've got SLAs for request response. We've also got SLAs for price streams. So individual price streams can go stale. You can see USD JPY at the top. We can turn it on and off, which is what Lee showed. We can also stop it ticking altogether, and we wait. If I actually...
You've got it off screen, Matt. You want Euro JPY?
Click the button, USD JPY goes stale, and the server tells us that, the application, the user interface tells us that something's gone wrong. You can't trade on a 4-second-old price. You just won't succeed, so we're not even going to let you try. Sorry, it's unavailable. In a real application, we would have a phone number here, and you could pick up the phone and call and figure out a way to actually do the deal. But as we said, I seem to have lost the ability to click. As we said, there's silences, so timeouts, messages going missing, messages arriving out of order, but also just failures, right? Just things shutting down altogether. And we can stop the server. So the server for this WPF application is running in this other WPF application. If we hit stop, we've torn down the process, the TCP connection has been reset. Todd was talking about this yesterday, and it comes back to life because every click I do is turning into 2 clicks. And it stops, everything shuts down. Now, if we weren't properly resilient to server failures, and we had what I like to think of as a hard dependency on some distributed system, so we're making synchronous method calls, we're blocking, waiting for a response. Right now, the application would be totally blocked up, nothing else will be happening, and we'd probably have to shut it down and restart it. But that's not what we're doing here. We've got slightly more sophisticated understanding of the problem. We don't have a hard dependency on this distributed system. What we have is a soft message-based asynchronous dependency. So when the server comes back up, the UI is polling quite frequently, because you saw how quickly it came back to life there, and it reconnects, resubscribes to all the currency pairs, and comes back to life. Again, it's not no nines of availability, but what it is making sure the application doesn't need to restart. And you can only get there, you can only get to this world with message-based asynchronous user interfaces that understand that asynchronous boundaries exist and that we can't have synchronous method calls into distributed systems sitting somewhere out on the network. It just doesn't work. We won't go into it now, but if you come to the workshop tomorrow, we can talk more about how you go about building systems like this that don't fail when a data center goes down. And when I say don't fail, I mean the user doesn't even notice. We just keep going. You do it with wasting a bit of bandwidth, but if your SLA is that you always have prices on someone's screen, then you need to pay the price. And we can talk about that tomorrow. Was there anything else that we wanted to talk about for resiliency, Lee?
Just the other thing is that if we mentioned, Jonas mentioned event stores, that becomes really interesting for things like resiliency around your trade blotter. Here we might have up to event ID 10. When we lose connectivity to the server, comes back up again, we can just say, hey, I was at event 10, send me the changes. A lot easier than saying, hey, I lost connectivity, send me everything again, I'll figure out the difference and then stream the rest. So event stores can greatly simplify this kind of stuff, and it's amazing to watch your code base to shrink when you're using the right tools.
So, elasticity. Now, Martin asked us to talk about user interfaces from the perspective of the Reactive Manifesto. I think we kind of got it for message-driven, responsive, and resilient, but when I think of Elastic, I think of all the talks we've heard over the last few days where we scale up thousands, hundreds, tens of thousands of machines, turn them on, rebalance processes so that we're making the best use of computing with Mesos, things like that. To be elastic, we need to avoid contention points and we need to avoid central bottlenecks. We've got both of those things and we can't do anything about it, really. There's a single laptop running a single application. We could scale Lee, we could put multiple instances of them in different places around the world, which is one way of getting resiliency.
Well, we do that already.
We do that already, yeah.
We've got a claim in Australia.
But it's not something that we can do. It's not always a business process that allows us to, we don't always have a business process that allows us to do that. Sometimes Lee really is the only guy that can make the decision. So we can't do anything about it. But we talked about conflation earlier, and really the problem is that the technical resource that we have, that we're sharing out amongst our application and the rest of the machine, all the other applications that are running on our dinky little laptop there, are the shared UI thread, so single-threaded UI applications. Some of the things we've done are quite straightforward. There's responsiveness and resiliency, but actually there's a bit of elasticity in it as well. The last render mode that what's our time like?
Constant rate. Shall we skip past constant rate?
Yeah.
We'll talk through it, we just don't need to.
We'll talk through it, yeah. When we've got prices coming in to the UI, again, excuse my terrible visualization, we've got prices arriving, and instead of being driven, so if you conceive of this little yellow bar as the amount of time the UI spends updating the screen to display that latest price, changing 6s to 7s, so on and so forth. That technical change in mutable state that we have to live with because we've got a UI and only one screen. We've got prices coming in, and we've gone to render at a constant rate. So this is exactly what computer games do. We have simulations, physics models, ballistic models, inside a computer game. They run at very, very high frequencies. They have a very fine amount of precision. But because our screens only update at 60 frames a second, which is what we talked about earlier, we actually only figure out where the bullet is or where the soldier is or whatever other game you're playing. All sounds really violent, but it's not necessarily the case. We only figure out where that thing is in the virtual world 60 times a second, and that's where we draw it on the UI. That's where we run our collision detection algorithms over. The same thing here. We are rendering at a constant rate as we go across the UI. So only the last of those currency pairs that have arrived, so the green and the red, I guess there, render. Here, these are the guys that render. These ones don't get a chance. They just get thrown away. They are replaced by the one that arrives later. Now, conflation is typically, it's a good approach, and this is taking it one step further, where we're removing the rate at which we update the UI from the amount of the information rate for streams coming into the UI. So if we just naively didn't do this and had 100 price streams, even if we were conflating down to 1 a second, we'd still have 100 updates a second. That would probably be fine, but the point is that it's unbounded, and we keep scaling, and we lose the ability to have the user interface respond and look good and mouse over and all these things. We've got this shared constraint that we're taking too much time on. Shared resource that we're taking too much time on, I should say. So rendering is something that it takes some amount of time, some finite amount of time, but still some amount of time. And it can take too long. If we say we have a budget for rendering prices on the UI of, say, 50% of real time, and we find that the amount of time we're spending rendering is doubling because we've got not just 3, but 6, 9, 18, 30 different streams of data all competing for time to render on the UI, what we can do is we can back off. So this render frame here, we can just stop doing it. And if you have a look inside Reactive Trader, there's an implementation that does exactly this. You can configure how frequently you try to draw, and what you can do is look and see how long it's taking you to draw, and if it's taking you too long, you stop and you don't try to do it again until further in the future than you usually would be, which lets the rest of that resource get used by other parts of your application. We won't do the demo. Have a look at Reactive Trader. It's a subtle concept, but when you're building these sorts of applications, it's something you need to worry about. But what we'll come back to now, before we jump off the stage and everyone can get some lunch, is those asynchronous domain models that we talked about earlier. So do you want to switch over to the code? So back in the old world of CRUD, where we had object graphs that came across from the database and loaded into our UI, and you could dot through them, and it was all synchronous and all easy to understand, well, CRUD is dead, right? We don't have CRUD anymore. What we've got is creates and reads. And reads are not reads, they're streams. So we can create data by sending a message, and then we just get streamed back the changes at some point in the future. So it's all asynchronous. But what does that make a domain model that we all kind of understand and can reason about in our heads when it's synchronous look like? How does that work? So Reactive Trader is built on an asynchronous domain model, which is something we'll walk through now. So Lee, if you type, I'll kind of talk about what we're doing. So this is the API that Reactive Trader runs on. This is just LinkPad, which is a .NET application for running small bits of code, kind of like a REPL for .NET, if you will. We've got a connection to the local server, and we've got a connection status stream. So all this is based around RX. Ben knows this stuff. I'm sure lots of you guys know about RX and the various other reactive streams from the Scala guys. So what we've got here is a stream that if you switch over and stop the server, Lee,
Yep.
we'll see is actually the real thing. You're going to use a mouse?
Yeah, so you can see, hopefully, it's quite small down there, I'm just trying to make that larger, that you can see that down the bottom here it's reconnecting, okay? So we jump back, start the server, and hopefully it's quite subtle, you'll see it change from reconnecting to reconnect dead.
Hit start again, it's not actually started. There we go.
Thank you. So reconnected.
So we see reconnected again. So this is the real API that has got some state and an asynchronous connection to the server, and it understands that connections are transient and ephemeral, and that's okay. We don't have to shut down the API, recycle it, throw away the process and start it up again. That's not what we have to do. So what we're now going to do is interact with the domain model of Reactive Trader. And understandably, the domain model of Reactive Trader talks about price streams or currency pairs, price streams, and execution requests. And we'll walk through those things and figure out what it looks like when you actually program against them. So this syntax here is query comprehension syntax. It's a .NET link thing, but I'm sure you guys have all seen similar things. It looks a little bit like SQL that Andy was talking about just before. It's kind of like SQL. I don't think of it like that, but people do. It's easy to reason about. So what we're doing here is we're going off to the server, making an asynchronous request, sending a message and getting back a response, wrapping up that logic in Rx and getting out a stream of currency pairs. This is a set of all the currencies we're allowed to trade on. We're going to pull out each one from the set, filter by the currency pair we want, euro dollar. And when we get a currency pair, when we find the currency pair, this line of code, we're going to dot into it and hit this price stream. Now this price stream isn't a normal property, it's not an event stream, it's an asynchronous event stream that when you subscribe to it, will go off and make a connection to the server and start responding and retrieving prices for that currency pair. So we're not polling for changes, we're having the server push them to us, but we're registering our interest in this price stream by first getting the currency pair, finding the one we want, executing on the price stream, and yielding it onto the UI. So if Lee runs that code, we've got a bidded and ask spread here telling us the prices of euro dollar right now in the market. And if we went over and increased the throughput, we'd see what we expected to see. If we made the stream stale, we'd see what we expected to see. If we stopped the stream, stopped the currency pair streaming, we'd see that stream terminate and no longer be available. So all of the concepts of the application are replicated in the domain API. So we've seen it stop ticking. Fantastic. And it went stale as well, which is great. But now, it's not enough just to have a stream of prices. It's only interesting if we can do something with them, right? So what we're going to do now is, in effect, place an order. Place a algo order, because we're going to have a computer executing it for us. So this is the sort of HFT stuff that people get up to when the markets are moving really quickly, when we write computers that trade against each other, write software that trades against each other, I should say. But in this case, it's Lee. He's not very good at it, so we don't let him do it very often. But we're going to ask for some prices from the euro dollar stream. We're going to, again, filter on that price stream. And you can see here that this is all just, it reads really nicely. So the asynchrony of our domain model isn't gone, it's encoded in the domain model. We don't have to worry about refreshing and polling or doing anything like that. The underlying implementation takes care of all of that and pushes it to us. So Lee's placing an order, which is effectively what we're doing here. Whenever we get a price, an asking rate that is less than the most that we want to pay, so let's say we're buying tickets to an event, someone's selling them for $20, but we actually only want to pay $19, well, we're going to put an order into the market and where we say, when we see a price that's less than 19, bang, purchase, make the trade straight away. And we leave that running overnight, we go to the pub, we do something else, and our system, little algo trading engine is running away, buying us tickets for sports events, which is exactly what we want. So that looks like an execute request just down there.
Yep.
For €1 million. Are you sure about that, Lee? We're doing a trade for €1 million, and then we're going to select out the trade status, and that's it. Lee's going to take one on the order, an RX concept, because we don't want to buy more than once. As soon as we've bought once, we want to stop. But again, the concepts of stream processing are mapping to the business, right? So we've got a asynchronous domain model that really easily maps to the way that we think about our business problem. If we hit this, we should see,
And we're at the mercy of a random walk.
and we're at the
moment,
mercy
so-
of a random walk that may or may not get us where we want to be. Did you test this beforehand, Lee?
Sure.
So maybe we'll see an execution, maybe we won't, maybe we need to stop the server. But the point is that we've got a asynchronous domain model that is going off and retrieving data and having changes pushed to it that totally negates the need for us to have this sort of CRUD-based ORM world where we've pretended that an object graph is actually what's living in our database. Actually, what's living on the server is streams, and this API lets us deal with streams as a first-class concept in our asynchronous domain model. Boom, order
Put
is
it
done.
in the money.
We're the proud owners of $1 million worth of euro. How very exciting. So that's asynchronous domain models, and that's the sort of thing that you need to have to build event-driven user interfaces that respond and look like Reactive Trader. And that's the sort of stuff that we build for the financial services. So that's us, that's the talk. Q&A or lunch? Lunch, there we go.
Feel free to come up and say hi.
Thank you very much, guys.